Okay, good afternoon, and thanks, Steve. Thanks for NVIDIA for inviting me to come and give this presentation. So I'm going to follow on a few comments that were made in previous talks, especially the last three. Jeff Vedder gave a few introductions for some of the activities that we've got going on at Oak Ridge. And again, you'll see some of the things that Professor Wu just talked about at Illinois. When they moved from Blue Waters, from an IBM to Blue Waters with Cray and AMD and NVIDIA. So I'll make a few comments based on that as well. So the vision that we have at Oak Ridge National Laboratory is multifold. In particular, we believe that part of our vision is to provide the world's most powerful open resources for scalable computing, simulation, as well as data analytics and infrastructure for science. We have a well-defined path. We haven't had to suffer some of the consequences of NCSA of late. We have a well-defined path for moving forward in this area, and we've been working with Cray and AMD and now NVIDIA for quite some time. We do believe that we would like to find talent from all across the world, and so I'm here today to not only talk to you about what we're doing at Oak Ridge, to also indicate to you that we're looking for that next generation of computer scientists or computational scientists to assist us at Oak Ridge National Laboratory. So we've hired on the order of 60 to 70 people since I've been at Oak Ridge. So this would be for the past 9 years. We've hired 60 or 70 PhDs and master's level people in computing and computational sciences. We do deliver leading edge science across a broad variety of venues, in particular for the Department of Energy, but we also do work for the National Science Foundation, as well as for the National Oceanographic and Atmospheric Administration. We do work with industry. I'll have a few comments about the activities that we are doing with Cray and with AMD and with NVIDIA, as well as some of the software vendors that Jeff mentioned previously. And we are providing a unique multi-agency collaboration space at Oak Ridge. And of course, education and training is very important. We just announced this past year and have our first class in conjunction with the University of Tennessee. We have a program, the Bredesen Center for the Interdisciplinary Research in Energy Sciences. And so we just have our first 20 PhD students in this area, and we're looking to field several students in the area of computing and computational sciences at the Bredesen Center. Partnerships, and this is an important aspect of what I'll be talking about. Partnerships are extremely important to us. We talk about international partnerships, multi-agency partnerships, multi-institutional partnerships, multidisciplinary partnerships, industrial vendor partnerships, partnerships between experiments, theory, and simulations, as well as facility and R&D partnerships. And all of these partnerships are very, very important. We talk about, I'm a computational chemist by training, and so when I talk about partnerships from a multidisciplinary perspective, I mean the partnership between the theorists as well as the computer scientists and the mathematicians. This is just one example. We have many partnerships, and we can't get to the Exascale without all of the partnerships that we have in place and ongoing. Some of those partnerships from an international perspective were already talked about. Jeff Vedder talked about the IESP, and that's been going on for quite some time. And some of the partnerships that we have at Oak Ridge have been going on for a long time, but each one is very important and is necessary to do the heavy lifting required to get us to Exascale. You've heard already some of the challenges that we have in front of us, and I'll elucidate on a few of those, but it's really daunting. And for us to get to Exascale over the next 6 years is going to take a unified approach. How do we execute the vision that I mentioned? And so the vision really is one of scalability. You've already heard some talks about scalability, and you've heard the hard questions about, do you think we're going to get there? And we're always in the process of talking about scalability, and we think of hardware as scalability and software scalability, but it really starts from the base infrastructure that we have. If we don't have the scalability and power in cooling and networking and the hierarchical storage and cybersecurity, if we don't have all of that scalability, we can't even begin to think about our systems, our hardware systems and our software systems. And so scalability is a necessary component. So at Oak Ridge, for example, we have 25 megawatts of power coming into our open unclassified computing facility. We have 6,600 tons of cooling. We don't typically think of those things when we talk about the next generation of exascale computers, but it's a necessary component. We talked about the fact that many of the machines that are fielded today require many megawatts of power. Okay? Now, we aren't going to build computers that take gigawatts of power, nuclear power plants to run our computers, so we have to do some designs of our architecture in order to be able to accommodate the kind of power infrastructure that we have. But we need scalability in our power. We don't want to build a new, Jeff Vetter mentioned the fact that we had to build new buildings around our computers. We don't want to have to continue to build a new building around the next computer. At Oak Ridge, we have 25 megawatts of power coming in. We hope that we don't have to go much more. Okay, we have to build new buildings in Illinois, new building in China around Tianhe 1A, around the Japanese computer against the K computer. We have to build new buildings, but we can't continue to build those new buildings. We have to have scalable infrastructure and the ability to scale to that next generation of computer. We've already heard good examples from Professor Wu at Illinois about scalability with regards to tools and middleware. Okay? And we know that we have to go a long way from where we are today. At Oak Ridge, with Jaguar, we have 230,000 cores that we have to program, that we have to make our applications scalable to. We already know that if we want to build a supercomputer out of these kinds of processors, this is about a 15 megaflop computer. Okay? If I want to build a petaflop computer out of a 15 megaflop computer, how many of these do I need? Okay? About 1 billion. If I want to build an exaflop computer, I need how many? 1 trillion. Okay? It's going to be the scalability of these kinds of systems, of an exascale system built out of these kinds of tools. And Steve Scott, working at NVIDIA, his Tesla program takes you from these kinds of systems, from cell phones, all the way up to supercomputers. And that is a scalability challenge. We have to understand what the scalability is. And many of the things that we're doing in moving from a Jaguar system of 230,000 core processors to that next generation, and I'll talk a few minutes about Titan. When we take a socket of an AMD out and put a socket of an NVIDIA in, we're moving from something that looks like a 16-core processor to something that looks like a 512-thread processor. Okay? And so my scalability goes from 230,000 to 10 million. That's a huge challenge when we talk about tools and middleware. And then we have the layer of algorithms and analytics. Okay? And so when we think of the scalability there, we know we have the same challenge. We heard some about kernels that we have to develop, whether it's a matrix multiply, a DGEM, or some FFT, or these kinds of things. And those have its own set of challenges because the application developer really thinks about algorithms, and these kinds of tools are very important when we think about the application and getting the application to scale. And of course, we have applications that we have to worry about, and we have to worry about co-design of those applications with the next generation of hardware. It's very important from a scientific and technical leadership perspective that we are at the very bleeding edge with regards to computing and our compute capability. Scientific leadership goes hand in hand with the technology that we're deploying in terms of our computing and computational sciences. And this is something that drives us all, whether or not we're from the US or from China or from Japan. We know that we have a target out there in order to lead in computing and the technology, because leadership in science and technology goes hand in hand. And so it's very important for us to stay out there, and why we strive to have that next generation of leadership in computing. And so at Oak Ridge, we've been in computing for about 50 years. When we talk about back in 1954, Oracle was a computer, and the OR stood for Oak Ridge. So we've been in computing for about 55, 56 years, and we've been going on this path. We have a long history of high-performance computing, and that history is something that we've been able to leverage on over the past half-dozen years as we've embarked with the Cray platforms, and where today we have 3 of the largest computers in the world. These are all Cray computers. We have Jaguar, which is the Department of Energy's largest computer. We have Kraken, which is the National Science Foundation's largest computer. And we have Gaia, which is NOAA's largest computer. And so we have 3 very large systems at the Oak Ridge National Laboratory, and these large systems are all being used to do science. and they're all being used to do science that enables us to go into that next generation in conjunction with our experimental colleagues and in conjunction with our industries in order to solve those kinds of challenges that are important for us from a scientific perspective. This was hit on a little bit, but I think it's extremely important that we keep in mind that a system that we put in place requires a balance, a certain balance, and that balance is defined by the applications that we're actually running. Okay, and the kind of machines that I just talked about from NSF or DOE or NOAA, they all have different kinds of mission requirements, and each requires a different balance. Okay, Jaguar, our Department of Energy's largest computer, is a 2.3 petaflop machine. We configure these machines similar to how you think about configuring your laptop. Okay, you buy your laptop and you say, I need a couple of gigabytes of memory per processor. Okay, we do the same thing with our DOE machines. We look at our applications that we're running. You look at your applications on your laptop and you say, I'm going to run Microsoft, or I'm going to run, whatever Fortran compiler you might need, or a CUDA compiler, or whatever, and you configure your laptop appropriately for that application mix that you are running. And we do the same thing. So when we look at the applications, whether it's climate or NAMD for biology, NWChem for chemistry, LSMS for materials, DCA++ for superconductivity, etc., we look at those applications and we build those systems to do those applications very efficiently. And so on Jaguar, we have our target was 2 gigabytes of memory per core. So on Jaguar, we have, now that we've done an upgrade, we have 300 terabytes of physical memory. And then we heard that we have to worry about getting that physical memory off of the machine onto our spinning disk. And so we have 10 petabytes of spinning disk. But that's not the end of the story, because we need to be able to move that data from that physical memory to the disk. And so really the balance is the 250 gigabytes of memory, or 250 gigabytes per second of bandwidth we have from the memory to our spinning disk. And then we have to worry about things like hierarchical storage and the network bandwidth. So it really is about balance. So over the last half dozen years, we've increased our performance at Oak Ridge by a factor of 1,000. And if you think about it, that's exactly what we need to do again in order to get to the exascale. We need another 1,000. So we've gone from a 3 teraflop machine back in, you see on the diagram here, back in 2005, we had a 3 teraflop Cray X1. And we've gone from a 3 teraflop machine to a 2.3 petaflop machine in Jaguar today in a half dozen years. We have to do another 1,000 in the next half dozen years. How are we going to do it? And that's really what the Exascale challenge is all about, because there are many challenges with individual components. But I can tell you that we have already today sustained petascale performance on many applications. So it's quite doable. You get a 1,000-fold increase in performance, and you can get a 1,000-fold increase in performance with the applications. Here are 5 examples of applications that we already have running at Oak Ridge at over a sustained petaflop of performance in chemistry and in materials, in nanoscience, superconducting materials. All of these are running at a sustained petaflop of performance. Well, over the next decade, we've got to do another 1,000 times of performance improvement. And in order to get that, we need 1,000 times performance improvement in order to actually attack some of these problems that we have. For example, in climate change and in many of the areas of energy production and the use of energy and national security. These things all require more compute capability in the next half dozen years than we have today. And even in the various basic science areas, we have good examples of applications that will require an exascale of performance. Now, if we look over the family tree of computing, this is an interesting illustration, because the question was asked by Steve, or someone asked the question, do you think that we've already hit the major challenges where we have to ask the application developers to build a new compiler or go to a different language? All right, we've already gone through several of these. Okay, so our colleagues that are in chemistry or in climate have already had to port their codes or rewrite their codes from vector to large shared memory to small shared memory per node to many processor homogeneous systems. And today we're here talking about many processor, heterogeneous systems, and in each case we've had to ask our colleagues to rewrite their codes in order to get the maximum performance that they can on these various platforms. Okay? Do I think we're done? No, I don't think we're done. Okay, I think there's probably going to be another rev of these kinds of architectures that are going to be required for us to get to that next generation of supercomputer at the exascale. We're going to be asking our colleagues to write yet another type of code. But the good news is that all of the parallelism that we've exposed in moving from the kind of systems that we're going from today in Jaguar, a homogeneous kind of many-core system, to a heterogeneous many-core system, the parallelism that we've exposed, we can take advantage of, and actually our codes will run more efficiently even on the earlier generation of applications or on the earlier generations of architectures that we see. So what does the Cray XK6 node look like? Well, I mentioned to you before, we've already started this upgrade. I'll say more about that in a few minutes. But what we've seen is that you take a processor, you're going to take half of the processors out of Jaguar and replace half of those processors, one socket per node, with a AMD Interlagos processor, okay, 16-core processor. And then you're going to take half of the sockets, so one socket per each node, and replace it with a GPU processor, okay? And so Jaguar, as we know it today, is moving to a new system called Titan, and this is a cartoon of that. And so we're moving from, now think about the parallelism, we're moving from a 6-core socket to a 16-core socket, and from a 6-core socket to a, basically think of it as a 512-thread socket or of NVIDIA Kepler. Okay, we're going to start with some Fermi and then move to Kepler. And so Jaguar really looks like 18,000 nodes, but now 18,000 Interlagos 16-core processors and 18,000 Kepler processors. And so you can imagine that the amount of parallelism that we have now with Jaguar is on the order of 10 million way parallelism as opposed to 230,000 way parallelism. So here's an example of what we think we will have with Jaguar. Okay, so if you look over here, you see that we're going to put the Fermi chips, a few of the Fermi chips, not a lot of those, in by the end of this year, and then we're going to be putting Kepler chips in by the end of, or hopefully in the fall of 2012. Now, we already have applications that have been ported and are running on a Cray XK6-like architecture. These are architectures like you've heard discussed already. So we have a half a dozen applications that we've been working on for quite some time, and we actually have whole applications running now on these kinds of nodes as opposed to just kernels. So you can see we have material sciences, we have groundwater modeling, we have combustion, we have climate, we have molecular dynamics, and we have nuclear energy codes all running on these kinds of heterogeneous nodes. Now, we know that with our Department of Energy priorities that we don't need Exascale for everything, all right? So we need Exascale for certain applications, for certain science purposes. But Exascale is not appropriate for all of our engineering needs. We need a whole system, a whole ecosystem of compute capability. And so I'm not here to tell you that every application needs to be ported to an Exascale platform. We need a healthy HPC ecosystem that will allow us to target our applications to the right hardware systems. And so our engineering applications many times don't need the kinds of Exascale systems that we would have in place, but many of them will. Cloud computing and clusters are also important. And then also the workstations that many of our colleagues use in order to do their software development as well as to run their applications are quite appropriate as well. So now for Exascale, you've heard some discussion about Exascale already, and we really think of all three areas being important to Exascale, the applications, the software, and the hardware. But the driver for Exascale really, in my mind, is codesign and uncertainty. And so let me just say a few words about codesign and uncertainty. Okay, what we're really after, what the target is for Exascale really is, what we think of is complex systems of systems. And so what do I mean by that? I mean, for example, that I'm thinking about full systems, whether they're modeling a nuclear reactor. Okay, so this would be a virtual reactor, if you will. It is a complex systems of systems that we are really targeting, and that's what we're approaching with Exascale. And so when we think about these kinds of systems, we need to be able to design these complex systems with our vendor partners, with our hardware partners. That's what Codesign is all about. What uncertainty is about is understanding what my error bars are in my application space. Now, when we have mathematically, we think that there's a rigor to uncertainty. We can use mathematics to understand what the uncertainties are in our applications. And so we would like to know what those error bars are. So if I build a virtual reactor and I want to understand what a new fuel rod might look like, or what that new materials for that fuel rod might look like, I would understand the characteristics of that material with the uncertainty required to build that new fuel rod. Okay, so we have a taxonomy. You've heard some of this. Some of our focused technology R&D is going to be done by private industry. Some of it's going to be a community response. IESP is a community response, and where we do a lot of our applied math and computer science. And then we have shared responsibility when we talk about the applications that are developed from a co-design perspective. I talked a little bit about this, so I won't dwell on it. We get as much performance out of the hardware as we get out of the software. So when I was in graduate school, I ran on a 1 megaflop computer, okay? And today we have a petaflop computer. That's 9 orders of magnitude more capability. We have the same 9 orders of magnitude increase in capability in the software. So in reality, we have 18 orders of magnitude more capability since when I was in graduate school back in 1983. That's a huge amount of increase in capability, and we have to think outside of the box in these application domains in order to understand how to use it. Middleware is the key to delivering that scalability that I described. Co-design is a key in order to deliver applications running on the next generation hardware. We have examples of co-design applications already underway. We have a co-design center around nuclear energy. We have a co-design center around materials under extreme conditions. And we have a co-design center that is also looking at the area of materials. And so co-design is extremely important. In the area of nuclear energy, we have a new consortium that's looking at this virtual reactor, so building a virtual reactor that will help us to understand how to burn new materials hotter, faster, more efficiently, and leave less waste. We also have the castle, which is helping us to understand safety requirements. And again, the target is co-design with uncertainty. Okay. Now we know that there's critical technology investments that have to be made for Exascale. We've talked a lot about power. We talk about power with regards to full system power. We've talked about the power required by Jaguar. And when we go into an order of 10 increase in performance, when we move to GPUs, that stays at the same power. We have to have another increase of 10 at the same power and another increase of 10 at the same power in order to get us to the Exascale. So significant amounts of work has to be done in power and memory. We know that we need more memory and we need more memory bandwidth. More memory requires more memory, and more memory bandwidth also includes a lot more power. Okay? These swim lanes and these notional targets for 2015 and 2018 were already shown by Jeff Vedder, so I won't talk about them. But our close collaborations with vendors are extremely important. At Oak Ridge, we've been doing this for several years and been able to increase our scalability and our efficiency by working with our vendor partners. And most recently now, we've started working with NVIDIA. We actually announced back in 2009 that we were going to build our next machine with NVIDIA processors. And so here I am today telling you that that machine is already under upgrade. I want to just leave you with one other concept. With regards to scalability. It's not all about the compute capability. Data is extremely important. We're seeing huge amounts of data being generated at Oak Ridge. We already have, we have a petabyte of data from our spallation neutron source, an experimental system, but we also have about 15 petabytes of data that have come off of our simulation environment. We also know that if we go to our social media, like YouTube or Facebook We have exabytes of data that are coming off of those. And if we think about sensors, all of those video cameras that you see on every street corner, for example, we have multiple zettabytes of data that are being delivered. And so we need to make sure that we're working on data as well as our compute scalability. We need good data analytics and good data reduction techniques that will allow us then to take advantage of these big systems that we're putting into place. And so at Oak Ridge, we are doing a significant amount of work in this area, where we actually take a lot of the social media principles and apply them to data, whether it's coming from experimental facilities or from our simulation environments. And so this is an area that we're extremely interested in pursuing. Finally, one of the things that we're doing is combining our experimental facilities with our simulation facilities. And the reason we can do this is that our simulation facilities have become on par with our experimental facilities. So now, the material that we're putting into our spallation neutron source, the exact same materials, we can actually model with our computers, and so we have the same system that we're actually modeling, that we're actually doing experiments on. And so from this perspective, it's been extremely important that we actually can do the kinds of systems, whether you're thinking from a simulation perspective or from the complementary experimental perspective, and get results with known error bars. And so finally, let me just say that I hope that the message that I leave with you is that it's extremely important to continue the kinds of partnerships that we have. And again, these are multi-institutional partnerships, these are international partnerships, these are partnerships with vendors, partnerships with the experimentalists. And so all of these partnerships are extremely important as we move forward to be able to realize that long-term relationship with our vendors in order to get us to the Exascale in that 2018-2019 timeframe. So with that, I'll leave you, and thank you again, Steve, for the invitation to come and speak.